Hi everyone, in this video we're going to talk about nuclear decay. So nuclear decay is a natural process that happens when you have something that's radioactive. So our radioactive elements like uranium, this is the natural version of it, 238. This is the not enriched. Remember U-235 was the enriched. So this is our natural version of uranium that just happens to be in the soil. It decays on its own if left exposed to the elements, and it will do this naturally over time. Each isotope, like U-235 or U-238, has a specific breakdown process that it goes through. And what happens here is it emits radiation. It emits radiation in the form of alpha radiation, like we had discussed, the helium nucleus. It can emit different types of radiation as well. It can emit what's called a beta decay, beta radiation. And this is where it's losing, let's see, I can't remember off the top of my head what it is. We'll cover it in the next video, but there's two different types of decays that are happening in this chart. In topic 11.3, we're going to go over the different types of decays and exactly what they are. The only one that we've learned so far is alpha, which is our helium nucleus. But what you're going to see in this chart here is uranium-238 goes through a specific process. Every U-238 atom will break down exactly like this because of how the atom's design is, if it's done naturally. So if you just let U-238 in the soil sit there for a while, it's going to break down into different elements. Now remember, we had said these heavy elements on the periodic table are unstable, and so they split into other things. One of the atoms that it's going to emit alpha radiation in order to turn into is this thorium here. So it will emit an alpha particle in order to turn into thorium. And that thorium emits a beta particle to turn here into Pa, which is, let's see, protactinium. Sorry, these are heavy elements that I don't normally talk about. It'll emit another one to go to a different isotope of uranium, and then it'll decay by alpha decay here to get down to radium and then radon. These are more common forms of things that we've heard. And what you'll notice is it keeps breaking down and breaking down and breaking down until eventually it gets here to lead. And lead is stable. So this is the process of our nuclear nuclear chemicals breaking down into a stable form. So once it's at lead, it's not radioactive anymore. It's not going to emit alpha decays or beta decays. Something you'll notice on this graph, though, this graph is plotting mass number, so that's grams per mole from the periodic table, versus its atomic number. The atomic number is the number of protons on the periodic table. So if we look at our, say it's a 238, and this would be 92. So this is your atomic number, and this is your mass number. So essentially what that is telling us is when we lose an alpha particle, because we're going this way and then this way, we're losing mass, so it's decreasing in mass, and it's also decreasing in atomic number. So we're losing neutrons and we're losing protons when we undergo an alpha decay process. For beta decay, you'll see that the mass number isn't going down on the vertical side, but the atomic number is going up, actually. So the number of protons is changing. So we're seeing here that with beta decay, our mass number stays the same, but we're gaining protons, which is really weird, right? So this is something unique that nuclear decay does. And we will talk about this in topic 11.3. The main thing to take away from this graph is that every single atom that is radioactive has a specific decay process that is specific to that atom. So if you had looked at, say, U-235, it'd have an entirely different process. So we use this natural decay process to do something called radiometric dating. You might have heard of it before if you've ever studied how archaeologists and paleontologists and stuff look at old artifacts and determine how old they are. So we use this in order to determine how old something is. Because it takes a really, really long time for radioactive elements to decay, that process that I showed you, the uranium turning into lead, takes a really, really long time, like 100 million years in order for that process to finish. So I was really, really off. Okay, so 1.5% of U-238, say in rocks, it's naturally in rocks, turns to lead every 100 million years. So what that looks like is in your rock you have uranium-238 atoms scattered about. There's a lot of other different types of atoms, of course, but uranium is mixed in there. And over time, every 100 million years, about 1.5% of those are converted to lead. So a small amount of them gets turned to lead. And so we can measure how much lead is in something in order to determine its age. Another thing to take away from this is that nuclear waste from power plants, that sort of stuff, takes a really, really long time to break down naturally, which is why we have storage facilities like Yucca Mountain here in the United States, where we store radioactive material to let it undergo processes similar to the one I just showed you. So that nuclear waste from your power plant goes through a process just like this in order to break down. It takes a really, really long time to do so. Eventually, though, that material will turn into something that is completely harmless and can be released into the environment, and because it is no longer radioactive. So this brings us to the process of half-life. Half-life is how we use this decay process, how we use math, in order to calculate how long it takes something to decay in order to determine how old it is. So let's take a look here at this graph that shows an isotope of cobalt. So this is cobalt-60. It is radioactive. This is a very weird isotope, and it emits, sorry. So normally the mass of cobalt is 59, so this is an isotope. It's heavier than it should be, and it decays with radioactive measures. So essentially what's happening here is over time, this is decreasing. So let's say you start with a sample of 10 grams of cobalt-60 isotope. And then after a half-life has passed, we have half the amount that we started with. We have 5 grams. And then after another half-life has passed, we have 2.5 grams because it's turning into other stuff, right? So it's turning into another isotope or another element entirely. So this is what cobalt-60 is remaining. And then as another half-life goes on, that gets cut in half. Another half-life, that gets cut in half, and half, and half, and half, and half, until there's literally like a tiny, tiny amount of cobalt remaining, cobalt-60 remaining. And so at that point, it's not really radioactive because there's so little of it left. So we use this half-life a lot to do these calculations. So the definition of half-life is the time it takes for half of a radioactive element to degrade into another. So this cobalt-60, I'm not certain what it's turning into, but maybe it's just turning back into cobalt-59. So over time, this cobalt-60 turns back into its non-radioactive parent atom. Something we observe from this graph is after one half-life has passed, that is the time in which half of the material that we started with is gone. So let's look at the equation for this and how we can calculate it. So this is the half-life equation here. I'm going to write it a little bit more in an easily understandable format. It's 0.5, and it's going to be raised to the t over t 1/2. Okay. All right. So this is what your half-life equation looks like right here. Now, the variables that are involved in here are defined on this slide. The amount of substance that is present at time 0 is NO. So in that previous example, we started with 10 grams. So that would be, say, like 10 grams. But the unit on this is moles, so you'd need to convert that to moles. So this would be moles, say, of cobalt-60 that we started with. So you need to take that 10 grams to moles. In T, here in this equation, is the amount of moles present at time does not equal 0. This could be any time that is chosen. Okay, so T is some number which will be selected or given to you. So T is the number of time. It's our time. Okay. So the amount present at time T, which is not 0. Okay, so T is our time. T1/2 is the half-life of the element. So cobalt-60 has a very specific half-life. It might be minutes, might be hours, it might be days. And so that's the time in which half of the substance is gone. Let's look at an example calculation using these numbers. So let's say for our cobalt-60, we started with 10 grams of it. And we're looking at a certain snapshot in time. And at that snapshot in time, the amount present that is currently present is 2.5 grams. Now, the time that it took for this change to happen is over a span of 10.54 years. The half-life of cobalt-60 is a known value. It's known to degrade by half over a period of 5.27 years. So we can use our half-life equation here in order to calculate any one of these variables. So in a problem, you'll have one of these variables that is not present. So they might say the current amount present is 2.5 grams, given that this much time has passed since the sample was present, and this half-life determined the initial amount that existed before the half-life passed, or something like that. Or it might say, given this initial amount, this time present, calculate the half-life if this much has changed. So these are each of these values here. So our initial amount is in 0, the time present at time 0, so that's your initial. The amount present at a given time, so that's in T, so that's the amount present at the given time here, which is 10.54 years. And then the half-life is a known value, so this is T1/2. So you could be given any combination of these variables. One of them will be left out, and you'll be asked to solve for the other ones. So remember that this needs to be converted to moles before it can be put into our half-life equation. And the units on our T and T1/2 can be any amount of time. It could be seconds, minutes, hours, days, whatever it is, but they need to be the same. So if T is given to you in years, then T1/2 also needs to be in years. Usually T1/2 will be given to you, and you'll have to find T in years. Usually T1/2 will be given to you, because that is a known value that you can actually look up. But say T1/2 is in seconds. Maybe this is a really fast degradation. Then the time that you calculate from this equation will also be in seconds. Okay, so make sure these match. That's very important. Let's look at an example here. So cesium-131 is a short-lived radioactive atom, or you might call it a radionuclide. That's normally what they use in medicine. They call it a radionuclide. Okay, so this is used to treat prostate cancer, and it has a half-life of 9.7 days. So remember that whatever your half-life is in is what your time is going to be in as well. So this question asks us to find what percentage of cesium-131 is left after 60 days. So we're good here on our time. It's in the same units, days and days, so we don't need to convert anything there. So let's write down our equation. In T over in 0 is equal to half, so that's 50%, 0.5 is like 50%, it's 50 over 100, is 0.5, okay, raised to the t time, which is 60 days, over our t1/2, which is 9.5, or 9.7 days. Sorry. So what it's asking to solve for here is the percentage of C131, which is an amount. So what it's asking us to solve for here is actually both of these numbers right here. So remember that in 0 is the amount that you started with. So say you started with 10 grams, you converted that to moles, and you ended after a while at 5 grams. Let's say you converted that into moles and you ended up with 0.005 moles. I'm making these numbers up, by the way, so just for the sake of what we're doing. Okay. And you'd find that this is 50%. Okay. Only half is left after a half-life is passed. Okay. Which is why we can say that 0.5, say your half-life is the same as the time that has passed, be 9.7 over 9.7, which is 0.5 to the 1. So they give you 0.5, which is 50%. So if your half-life is the same amount of time that has passed, then you have 50% of your initial radionuclide remaining. So it's asking you to find this percentage here. It's not 50% because these are not equal to each other. And I'm going to ask you to determine that amount. Okay, so how we solve this is 0.5. It's going to be raised to 60 divided by 9.7, which when I put that in my calculator is 6.19. So if I take 0.5 and I raise that, 0.5 raised to 6.19, then I get 0.014. Now, this needs to be converted to a percentage because we're assuming that, so we need to find what number this is over 100. That's how we determine our percentage. So in order to solve this, we can take 0.014 times 100, and that will give us our percentage out of 100. And we find that our x is equal to 1.4. So 1.4% is what's left after this cesium-131 has been inside the patient's body for 60 days. All right. Let's work a second example on half-life. So this one's going to ask us to solve for hours. It says, how many hours will it take until 87.5% of a sample of polonium, or a sample of radon, has become polonium? So this is a natural decay process where radon breaks down into polonium by emitting an alpha particle. And it's asking us to find the time that has passed. Time in hours. The half-life of radon is given to you here. It's given to you in days, so be very careful about this. Remember, this is a percentage. This is how you convert for percentages. We did this previously. And let's see, I think you're going to be solving for t over your t1/2. Okay, so let's work on this problem step by step together. The first thing that I'm going to ask you to do is to convert this percentage into a number that we're going to input for nt over no. So remember that 87.5% is 87.5 over 100. And we want to know what that is, so we simply put that in our calculator, and you're going to find that that is equal to 0.875. Okay, so that's the value that goes in for nt over no. So 0.875 is equal to 0.5. We're solving for time in hours, t, over our t1/2. Our t1/2 is down here. It is 3.825 days. So now we need to get t by itself. Okay, so let's take a look at how to solve this. I want a little bit more space. So right now we have t in our exponent, and we are trying to isolate t. So what is the inverse function that undoes an exponent in mathematics? So there are two options we can use. We can either use log or natural log. I'm going to use log for this one since natural log is specific to the value of e. So we can apply logs very easily here because we just take the log of both sides. We do the same thing. So the log is the inverse of something raised or an exponential. So 10 to the x is the opposite of log 10 of x. Okay, so these are opposite each other. One undoes the other one. So what we're going to do here is we're going to take the log of both sides. So we're going to take the log, and we're assuming this is log base 10. When I say log, it's log base 10. We're going to take the log of all this other stuff. Okay. Now, one of the properties of logs that you'll need to remember is that when we take the log of something, it allows us to take the exponent in the top and bring it down. That's what's really important about logs, is we're going to take this whole thing here in the exponent and bring it down. So it goes down in the front of our equation, t over 3.825 times log of 0.5. Okay. So it just takes our exponent up, brings it down in front of the equation. And that's all you need to remember about logs. That is as advanced as it is going to get with logarithms in this class, okay? All right, so go ahead and put this in your calculator and see what value you get for t. So when you put the log values into your calculator, these are the numbers you should end up with here. Now we need to isolate t by itself. So we're going to do our inverse operations to get t by itself. So because this is multiplied here, we're going to divide both sides by that, divided by 0.3. That gives us 0.19, which is equal to t over 3.825. Because this is divided here, we need to do the inverse operation to undo it, which is multiplied. So we're going to multiply by 3.825. Multiply both sides by that, 3.825. Okay. All right, and we end up with t equal to 0.74. Right. So what unit is this time n then? What you'll see is that our half-life is in days. So this is in days. But our question asks us to solve for t in hours. Okay? All right. So go ahead and use unit conversion to convert days to hours to find out how many hours it takes this atom to decay. So in order to solve this, we're going to start with our 0.74 days. And we know that for every 1 day, there are 24 hours. Our days cancel out here. So days is canceled by days, which is why I put days on the bottom and hours on the top. And so that gives us our final number times 24, gives us 17.7 hours. So that's your final answer for this problem. Okay. So the answer to this question is how many hours will it take 87.5% of the sample to become polonium here? 17.7 hours. That's how long it takes. So this will be the only time that you see logarithms used, and they'll be used in this limited capacity So you'll see problems like this where I ask you to solve for percentages or maybe solve for NT or NO. You don't need logarithms for that. For this kind of instance, the only time you need logarithms is when you have to undo your exponents. So log 10 undoes something, so let's see, some number raised to another number, okay? So log 10 of x undoes 10 to the x. It is the opposite. So you see how this x gets brought down here, it gets brought down here, okay? Which is the purpose of using our log to undo exponents.